Hello everyone and welcome to our channel Mootechie. It's wonderful to have you here as we dive into a fascinating topic from the world of pharmacy. Get ready to explore the science behind gels and jellies. Let's begin. Now let's start with a quick introduction to gels. Gels are semi-solid dosage forms. In them you'll find a dispersion of small or large molecules in an aqueous liquid vehicle. They produce a jelly-like consistency by the addition of a gelling agent. Gels are often formed by using synthetic polymers like Carbomer 934 and cellulose derivatives such as hydroxypropyl cellulose and hydroxypropyl methyl cellulose. Natural gums like Tragacanth, pectin, and agar are also commonly used in the formulation of gels. As per the national formulary, 6 specific polymers are used for gel formulation. Those are the following: Carbomer 910, Carbomer 934, Carbomer 934P, Carbomer 940, Carbomer 941, and Carbomer 1342. Here's an interesting fact: Carbomer 940 produces the highest viscosity, between 40,000 and 60,000 centipoises, in a 0.5% aqueous solution. Now here's a key characteristic of gels you should know. Gels may thicken on standing, forming what's called a thixotrope. This means they must be shaken before use to liquefy the gel again. A typical gel contains the drug substance along with water. It can also contain other solvents such as alcohol or propylene glycol. Since they often contain water, antimicrobial preservatives are used in gel formulation like methylparaben and propylparaben. They also contain stabilizers, for example editate disodium or EDTA. And importantly, medicated gels are prepared for administration by various routes for the eye, nose, vagina and rectum. Let's now look at how gels are classified. We have single-phase gels and two-phase gels. In a single-phase gel, macromolecules are uniformly distributed throughout the liquid with no apparent boundaries between the dissolved macromolecules and the liquid. In a two-phase gel, you have small separate particles. This is also called a magma. A classic example is milk of magnesia, or magnesia magma, which is a gelatinous precipitate of magnesium hydroxide. Next up, we explore the different types of gels. The main types we'll discuss are hydrogels, xerogels, and organogels. Let's understand hydrogels first. A hydrogel is a network of polymer chains that are hydrophilic. You can think of it as a colloidal gel, where water is the main dispersion medium. Hydrogels are highly absorbent natural or synthetic polymeric networks. They can contain over 90% water. Because of all that water, hydrogels also possess a degree of flexibility very similar to natural tissue. Common ingredients used to make them include polyvinyl alcohol, sodium polyacrylate, and acrylate polymers and copolymers. So what are hydrogels used for? Their uses are quite diverse. They are used as scaffolds in tissue engineering. They can act as environment sensitivity detectors. They are fantastic for sustained release drug delivery systems or DDS. You find them in everyday items like contact lenses. They are used in ECG medical electrodes, and even as a glue. Moving on to xerogels. A xerogel is an open network formed by the removal of all swelling agents, like water, from a gel. Xerogels usually retain high porosity, around 15 to 50%, and an enormous surface area from 150 to 900 meters squared per gram, along with very small pore sizes of just 1 to 10 nanometers. Here's a cool fact. When solvent removal occurs under supercritical conditions, the network doesn't shrink, and a highly porous low-density material is produced. This is known as an aerogel. And what are xerogels used for? Primarily in drug delivery systems or DDS. You'll often see silica aerogel and silica xerogel used for this purpose. Now let's talk about organogels. An organogel is a non-crystalline, thermoreversible material. It's composed of a liquid organic phase entrapped in a three-dimensionally cross-linked network. The liquid in this case can be an organic solvent, mineral oil, or even vegetable oil. These systems are based on the self-assembly of the structuring molecules. Where do we find organogels? In pharmacy, they are used as drug carriers for transdermal drug delivery systems or TDDS. They are also used in cosmetics for better application and stability, and even in the food industry. Now that we know the types, let's look at some commonly used gelling agents. There's quite a list. Acacia pectin starch, Tragacanth xanthan gum, alginic acid, which comes from seaweed, animal and vegetable fats like cocoa butter, gelatin minerals like bentonite and vegum, which is magnesium aluminum silicate, carboxymethylcellulose or CMC, and other cellulose derivatives. Carbomer resins, which you might know as carbopoles colloidal silicon dioxide, polyvinyl alcohol or PVA, and mixtures like petrolatum and mineral oil mixed with polyethylene gel. So how are these gels actually made? There are three main methods: the fusion method, the cold method, and the dispersion method. Let's start with the fusion method. In this method, various waxy materials are employed as a gellant in non-polar media. The drug is added only after the waxy materials have been melted by fusion. The mixture is then stirred slowly until a uniform gel is formed. Next up is the cold method. This one is interesting. First, water is cooled to between 4 and 10 degrees Celsius and placed in a mixing container. The gelling agent is then slowly added while agitating until the solution is complete. It's important to maintain the temperature below 10 degrees Celsius. The drug is then added in solution form slowly with gentle mixing. The liquid is immediately transferred to its final container and allowed to warm to room temperature. As it warms, it magically becomes a clear gel. Finally, let's look at the dispersion method. Here the gelling agent is first dispersed in water with stirring at about 1200 revolutions per minute for 30 minutes. Meanwhile, the drug is dissolved in a non-aqueous solvent along with a preservative. This drug solution is then added into the gel base with continuous stirring to form the final product. Now, let's shift our focus to a closely related topic: jellies. Jellies are transparent or translucent, non-greasy, semi-solid dosage forms. They are actually less greasy compared to gels. They are mainly used on mucous membranes for lubricating or antiseptic purposes. Jellies are also commonly used for lubricating surgical gloves, catheters, and rectal thermometers. And of course, vaginal jellies and contraceptive jellies are very commonly used. Why are medicated jellies so useful? Well, they contain a considerable amount of water, which makes them very suitable for water-soluble medicaments. Think anesthetics, antiseptics, and spermicides. However, this also means they are unsuitable for insoluble medicaments. They are easy to apply, and after the water evaporates, they produce a cooling sensation on the skin. And when the treatment is over, they can be easily removed by simply washing with water. So how are these jellies prepared? Pharmaceutical jellies are usually prepared by adding a thickening agent, such as Tragacanth or carboxymethylcellulose, into an aqueous solution where the drug has already been dissolved. The entire mass is then triturated in a mortar until a uniform product is obtained. Several gelling agents are specifically used for jellies. These include Tragacanth sodium alginate, pectin starch gelatin, and various cellulose derivatives. Let's talk about Tragacanth in a bit more detail. It's commonly used for the preparation of lubricating, medicated, and contraceptive jellies. For lubricating jellies, we use about 2 to 3% Tragacanth. For dermatological vehicles, about 5%. And for medicated jellies, also around 5%. A couple more things about Tragacanth. Tragacanth jellies are also sometimes called basurin paste. When Tragacanth is added directly to water, it can produce a lumpy product. So to get a smooth homogeneous preparation, dispersing agents like alcohol, glycerin, or a volatile oil are used first. Now on to sodium alginate. Jellies made with sodium alginate are used as lubricants and as dermatological vehicles. In lubricants, we use about 1.5 to 2% sodium alginate, while for dermatological vehicles we use a higher concentration of 5 to 10%. In these jellies, alcohol, propylene glycol, or glycerin are often used as dispersing agents to help with mixing. What about pectin? Pectin is a very good gelling agent. You might know it from its use in various edible jellies. It's also mainly used in dermatological jellies. Glycerin is often used alongside it as a humectant and dispersing agent. And it's important that pectin jellies are prepared with suitable preservatives. Now let's consider starch. Starch jellies are often prepared in combination with gelatin and glycerin. These starch-glycerin jellies can be prepared by a heating method or the fusion method we discussed earlier. Glycerin, when used in large amounts like 50%, can also act as a preservative and a humectant. And then there's gelatin. Gelatin is soluble in hot water. Just 2% gelatin can produce a jelly in a hot solution. Very stiff medicated jellies can be prepared by incorporating more gelatin. These jellies need to be melted before use. After cooling to a desired comfortable temperature, they can be applied with a brush to the affected area. The treated areas are then covered with a bandage. This dressing can be left in place for several weeks. Finally, let's look at cellulose derivatives. Methylcellulose and sodium carboxymethylcellulose are widely used for the preparation of jellies. These substances produce natural-looking and stable jellies. They afford good resistance against bacterial growth. And they produce a strong film on the skin after drying. To ensure quality, there are several evaluation tests for gels and jellies. The key ones are pH determination, drug content uniformity, viscosity and spreadability. Let's understand spreadability a little better, as it's a crucial property. Imagine a simple test, where a weight, let's call it M, is tied to an upper glass slide. The gel is placed between this slide and a lower fixed slide. L is the length of the glass slide that the gel spreads over, and T is the time taken to separate the slides completely. These factors help us measure how easily a gel can be spread on the skin. And that brings us to the end of our session on gels and jellies. Thank you. See you in the next class.